which is how far is a score from the mean squared on average. That's what variance is telling you. The average distance between a score and the mean squared, or the average squared distance between a score and a mean. Okay, so it isn't squared units, it's an average of squared stuff. Why are we squaring? Because if I just add this up, that's going to add up to 0. So we need to square it to get rid of that problem, and I'm going to just label this box x minus the mean squared. And I don't know if I can superscript that. So anyways, hopefully you know that means squared. All right. So what am I going to do? I'm going to say, all right, square this thing. And that's just that thing times the thing. So d2 times d2. So 0.8 squared, 0.64. And we'll do that trick where I just grab and copy it. And I've now squared everything. 7.8 squared, 60.84. Let's make sure it's the right thing. Yeah, it's doing d4 times d4. All right. Negative 3.2 squared, 10.24. See, all the negatives become positives when you square it, and that's why we're doing it. So now we have squared mean deviation scores. Let's go back to the equation. All we're doing now is computing the mean of those. Add them up, divide by n. Okay, so let's do it. So we're going to add up these squared mean deviation scores. The sum of them, n is still 5. I'll just copy that and paste it over. And then we're going to take the mean of that, which is now variance, and that'll be that divided by that. And we have ourselves variance, so I'm going to label that so that you know, okay? In fact, I'll even do something like, put it like that there, because that looks cooler. There we go. A little bit of formatting stuff. So the variance of these scores is 17.36. What does that mean? It means the average squared difference between each score and the mean is 17.36 points. Okay? So if these were ACT scores, these would be squared ACT scores. They'd be different from the mean on average by 17 squared ACT points, which is a little weird. We'll get back to that squaredness in a second. Okay? But that's how you compute variance. We just did it. The equation, I think we can agree, not so bad. If this is a population of 5, we have population mean, and now we have population variance. All right? Okay, I hope that's good. Okay, now I want to show you a few things about variance. I'm going to change the scores here. And I'm going to say that everybody has a 21. All right? All 5 people have the same score in this population. There's the sum, and there's the mean. No big surprise. If everybody has a 21, the mean's 21. What about those mean deviation scores? Look what happened to them. This is, again, why I like Excel, the live updating of things. They're all 0. And they're all 0 because everybody's score equals the mean. They're all 0 points away from the mean. And when you square all those zeros, you just get more zeros. And when you add them up, they sum up to 0. And when you divide by 5, they turn into 0. The variance is 0. All the scores are the same. Okay? So this should tell you a little something about variance. Variance is about differences in scores. It's not about how high or low a given score is. It's how different the scores are from the mean squared. Okay? Second, when all the scores are the same, variance is 0. So it can't be less than 0. All right? You can't square stuff, add them up, and get a negative number out of the deal. All right? So variance ranges from 0 to, who knows, it could be as high as, whatever, doesn't matter. And then third, let's do a different thing. I'm going to change all these scores from 21 to 0.21. And let's see what that does to things. Well, it changes the mean to 0.21, but the variance is still 0. All right, so you're saying that's a really weird example, Reagan. I don't like it. So let me go back to the original data set. By the way, I'm hitting Control-Z or Command-Z here to do all this undoing. We're back to the original scores. How about I add 100 points? Mean's 21.2, variance is 17.36. But I'm going to add 100 points to everybody's score. So it's 122, and 118, and 129, and 118, and 119. Okay? Obviously, the mean went up by 100 points. It used to be 21.2, now it's 121.2. but the variance stayed the same because variance isn't about how big or low the mean is. The variance is how different the scores are. And on average, the squared difference between each score and the mean has stayed the same. Okay? All right, that's variance, at least of the population variety. I'm going to take my data set back to the original data and leave it at that. What about sample variance? Because we don't always have populations. We frequently are dealing with samples, as we've already discussed. And if it's a sample of data, we don't know the population mean. We only know the sample mean. Well, this gets a little annoying, and we've mentioned this in class before. Here it is. Here's the sample variance equation. Notice we have the sample mean inserted where the population mean used to be. And now the symbol for sample variance is S squared, not sigma. Remember, Greek letters mean population things. Other letters mean sample things. So that's changed. But the other change that's kind of notable is instead of dividing by n, like you would normally think, we now divide by n minus 1. And if you're wondering why, the answer is you're almost better off not knowing. It's one of those weird stat things. It just has to be that way to work out. All right, so let's compute sample variance. The only change we'd make then is we would say instead of dividing the sum of the squared mean deviation scores by n, 5, divide it by n minus 1. So I'm just going to change that denominator to the number minus 1. See, now it looks like n minus 1. And hit that. And there's our sample variance. It's 21.7. Awesome. There, we just did it. Okay, so you know how to compute population variance, and you know that when it's for a sample, if we're going to call this a sample of 5, we don't know the population mean, we know the sample mean, and we have to make an adjustment to that equation and divide by n minus 1 instead of n. Small change, and obviously if you have a large sample, then it hardly makes a difference at all. In this case, it changed things all the way up to 21.7, all right? I'm going to go back, though. I'm going to go back to population variance. Okay, I hope that's clear. All right, one more thing before I hit stop on this video, and then I'll start another one. Just don't get too ahead of ourselves here. I'm going to break this up into 2 parts. Let's talk standard deviation. What is standard deviation? Standard deviation it's got to be the greatest twist on things. Standard deviation is just the square root of variance, okay? So if you have variance and you take the square root, you have standard deviation. And let's see, here it is. I didn't even put the equation for population, but it's the same thing. Whether you're dealing with population variance or whether you're dealing with sample variance, standard deviation is the square root of it. Okay, so for a sample, you have sample variance right here. It's S squared. That's sample variance. The squared sign tells you variance. You take the square root, and it's just S. That's sample standard deviation. If it was the population value, you'd have sigma squared. You take the square root, you'd have sigma. So you got to love it when the symbols actually mean something. All right. Why do this? Well, because variance is in squared units, and squared units are weird. That's why. Remember squared ACT points? Let's look at the data set. If these are people's ACT scores, that is the mean ACT score, and that is the variance of the ACT scores. This is in ACT points, the mean, but this is 17 squared ACT points. That's hard to follow, isn't it? I don't understand what a squared point is. It's not in the same metric as the mean or the scores themselves. So by taking the square root of it, I get standard deviation. So I'm just going to tell Excel to do that work for me. The square root function is SQRT. Square root of what? That. And I'm going to label this standard deviation. Okay. There we have it. So the standard deviation of these scores is 4.1665 and change. All right. That is the average distance, not squared distance, but the average distance between each score and the mean. It's a little mathematically just slightly different than that, but that's close enough for our purposes because we're back to the original metric now. The average score, the mean is 21.2, and the standard deviation is 4.1665. Awesome. We've got central tendency, that is mean, down, and we have variability down. 2 measures of variability, variance, and its twin, standard deviation. Okay. We compute variance, we take the square root to get standard deviation. If you have standard deviation and you want variance, you can just square it, obviously, but you start by computing variance and then you take the square root to get standard deviation. Okay, I'm going to hit stop here, and then I'll work on the second video, which you'll have already posted, so I don't know why I'm telling it to you like it's happening live.